Hello, my name's Eric Newman. I'm an applications engineer in Keysight's software sales organization. Today I'm excited to be here to introduce a new feature that will be coming in our next release of PathWave System Design 2021. We now have the ability to include the electromagnetic parasitic coupling effects into our system simulation, revealing new insights on how different metal-to-metal coupling might interfere with the carrier-to-interference ratio, what kind of power levels are being delivered to different nodes in the signal chain due to different coupling effects, and allow users to easily identify the root cause for unwanted degradation in signal performance. Okay, so for today's agenda, we're going to highlight the need for identifying these parasitic paths that result from component packaging, PCB layout effects, module packaging effects, and how it's important to capture these early in the design cycle. We'll understand how these impacts, if ignored, can really start to hurt your system performance, and how it's important to identify those biggest contributors to the problem so you can make corrections early if you can. We'll then review design flow, a simple design flow using an automatic gain control eval board from Analog Devices they've allowed us to use for general illustrations of this new feature. We'll go through how to extract an EM model using our latest RFPro EM simulation solution in ADS, and then we'll share some additional resources for you for future reference. Here we see a 28 gigahertz upconverter design that was worked on by a few of my colleagues for previous seminar material. I'll share a link at the end if you're interested in going back to review that material. What we found that was very interesting was after we started to put the lineup together and start to include some of the PCB trace losses and the mismatch effects due to the traces not being perfect 50 ohms, we were surprised how much the performance could be degraded. When we looked at the aggregate signal losses as we went across the signal paths compared to the ideal expectations, we were surprised that there was a bit more than we had anticipated and that we had to increase the power to hit our specifications. We are excited in the latest release of SystemVue 2021 to have a new interconnect parasitic model for you to use to capture insertion loss, mismatch loss, but also coupling effects across your signal chain. This is that upconverter I described earlier, but now in the latest release, we're able to use a more sophisticated interconnect model to capture the coupling between the different stages, but also obviously their insertion loss, their mismatch losses. This new feature allows the user to take in a multi-port S parameter set describing all of the electromagnetic interaction across these different nodes in the real hardware design, and then allow the interconnect model to intelligently define where it is connected within the SpectraSys schematic to the S parameters, allowing the user to really capture some very interesting insights about EM interaction with their system design at an early stage. To help users understand the design flow of using the layout modeling capability in PathWave System Design, we have a simple AGC evaluation subsystem from Analog Devices. The eval subsystem consists of an RF input connector going through some trace to a voltage variable attenuator cell, going through some more trace, going to a driver amplifier cell, through some trace to an output connector. There's also provisions to feed back the output power into a logarithmic power detector to form a closed loop AGC when using an error integrator amp to compare against a reference signal. This allows the user to set voltages and control a steady output power for varying input levels. The evaluation board, the earlier eval board, is shown here on the right. This is a section of the board in ADS layout. But you can see there's these sections in the top where the top metal was cleared away to make some connections, causing some inadvertent resonators. Some of the ground returns around the signal paths weren't ideal. There was even some issues with the thermal reliefs that were applied around the SMA connectors, the RF connectors. These parasitics can be represented in these layout interconnect models in our SystemVue SpectraSys simulation. Let's take a look at a simple example in SystemVue Early Access 2021. This is a simple two-stage design, again using HMC 985 voltage variable attenuator and the HMC 635 driver amplifier, both very wideband parts. And we have the interconnect models applied in between, which we can toggle, change between the final design, where they made some improvements to their RF layout in comparison to their original prototype design, where the grounding was not so good. And these resonators talking to each other, it seems. Before demonstrating the workspace, let's talk about the design flow a little bit. Where did these EM models come from for the prototype board and the final board? Okay, here we are starting in our favorite RF and microwave advanced design system, ADS 2021. This starts by doing a file import design. I point to the board file and hit OK and import it. It's that easy. You have to make sure you have the Cadence installation in the background so the tool has access to the module to help with the import. But a few clicks, you'll have the board imported. I wanted to set it up for an FEM simulation. So I set up a bounded substrate and I cut a portion of the board. And I created a bounded layout view with the ports applied as TML ports on the edges of the bounding condition. For an FEM simulation, that allows us to simulate these as waveguide ports on the edge of the board and help perfectly calibrate away any kind of parasitic effects due to the open-ended effect here. Give us a more robust, more accurate model. But I simulated this in our new RFPro tool, so I'll launch that. And here we are. I already set up the analyses and ran it. But we basically added our ports in. From up above here, we had the pins that were defined in the schematic. We brought them into the analysis with arbitrary names. We set up our simulation. Here I did an adaptive sweep over 3 subsegments out from 0 Hz to 32 gigahertz ultimately. I ran an FEM simulation using our new Gen 2 meshing algorithm for faster and more robust simulation. And I made sure to make automatic for a conductor edge mesh where there's coplanar waveguides applied in this design. I used a direct dense matrix solve for the matrix solve method. Ran the simulation. Afterwards, I was able to capture my S parameter results. Take a look at some of the different paths. This is the first design where there was multiple resonances and concerns. Then I was able to export away my S parameter as an S&P file. Could choose to downsample if you like. Export. I won't do that. I've done that. I exported into my temp directory. And I went ahead and opened the file. This is the prototype here. And just made a few quick little edits. You can see up in the port declaration area here, I went ahead and made sure that the names here were the same names that I was using as shown here, across the signal chain. So then I imported that data, file, import, sdata, and I browsed to that file location and imported my data into the dataset directory here. You can see it again, along with the names, those different EM port names. So let's go back to the SystemVue Workspace example. A similar process was used to capture S parameters for the final design, where they modified the layout to have better RF grounding in here, so we can compare performance differences. Right now we're looking at the performance of the final design where the conversion gain's rather flat. The estimated carrier to interferer ratio up here looks pretty good across frequency, and it looks a lot better across the cascade now. But let's take a careful look here. I'll show you what's in here. So modification of something you're not used to probably seeing up until now, until the new release, is the use in the system analysis controller under paths for adding a path that's a layout modeling path. So we go into this and click Edit. You can see for path type now we have a fourth selection called layout modeling. We select layout modeling, we can point to the data that we want to simulate. Let's change this from the final to the prototype. So I'll go ahead and point to the prototype. I have those both imported into the workspace. Now I'll go back up to the schematic, go in and double left click on one of the interconnect models. And you can see in here, we can change the definition for the model directly here, or we could go and use this interconnects table. I'm going to use the interconnects table instead. So I can go up here and say, okay, what's my data set that I'm simulating? And I can apply the proto as the new data set that I want to simulate. And then one more click and I'll go to apply to all. Changes the other interconnects. If we now go back to the schematic, we'll see, well, we have an interconnects tab down here now because we've created it when we invoked that GUI. But we can see over in here now these guys are all pointing to the prototype for the file set that will be simulated. Okay, so let's go back and simulate that, and let's just look at some of the basic results. I'm going to run the analysis direct in the workspace tree. You could also run all analyses using the green arrow up at the top. So let's take a look inside this data folder. What do we have for some results? Well, in that setup for the layout modeling, we went ahead and we enabled these table of common EM measurements and table of individual EM power contributions. And that automatically generates these tables here in the data set. So we can come in and take a quick look. Okay, what's our desired channel power? We're feeding minus 20 dBm in at 20 gigahertz right now. As we go through, we can see some attenuation through the VVA. There's signal loss through the traces. We come through the driver amplifier, we see some amplification, but then some further loss on the output traces. But more importantly, we're seeing what kind of contributions we have from other nodes, coupling back, leaking to the different nodes within the signal chain. And we can look at this estimated packaged power as an absolute value, or we can look at the contributions relative to the desired channel power and calculate a ratio or carrier to interference ratio. And we can see here in the carrier to interference ratio, we have a pretty poor value on the midpoints here around the VVA out, the driver input. Those seems to be the biggest problem areas for this design. We can come back and we can look at the estimated carrier to interferer ratio versus frequency and run a sweep. So this is using the old data. I'll go ahead and rerun this now. Using the prototype data where we have some resonant issues. And now you can really quickly see at different frequencies the problem's worse than others. Some frequencies it's not so bad, but some of those resonant frequencies we really have some issues to worry about here. So I encourage you to explore this example, look at the README file, go through the steps. We have a few different sweeps set up here. We've also set up a sweep on the gain control select. That was done using a little bit of equation wizardry provided to me from the great Dan Evers. But if we look in these different equation blocks in here, there's one for the source control, but there's one for the VVA control. This voltage variable attenuator, the data set that Analog Devices provides is over pretty fine steps over a huge array of control voltages. I selected the lowest insertion loss range here, but you could modify this file list to look at different parts if you have an array of S parameter data, and then use a select variable here to go through and select which S parameter data set you actually want to run with the data. So it allows us to run sweeps here versus our gain control setting and look at the actual conversion gain at a given frequency here. This is using the old design, and you can see we're lacking some max gain here at the output and resulting in max output power. That's because of some of the poor performance at this frequency. Then run it at a different frequency here. This is a little further off away from the resonance, so we get a little bit more gain back. Or we could fast forward and compare it back to the final design here and rerun that sweep. See that we're getting further improvement, achieving higher output power here at the max gain setting. Okay, as promised, I wanted to provide a few additional resources at the end here. The first two are good for those that want to learn the RFPro interface that I briefly showed in the ADS platform, help you get started using the tool, take advantage of some of its efficiencies. I also have eval request if you'd like to get on this PathWave System Design. You don't already have a license, you can request an eval from the link here. And then several other important links below. Our friend Anurag, he has done some great YouTube channel videos to help people learn the different tools. Analog has several good videos on using the RFPro interface and using SystemVue, especially for new users. And then the AE Tips and Tricks channel, there's a lot of different new how-to videos there to look at, as well as on our Keysight EEsof EDA channel. And I always like to recommend to users to go to the Knowledge Center. There's a lot of good stuff there. Anyways, guys, I hope you enjoy this and look forward to generating more material in the future. Take care.